Buenas tardes. So I actually gave several suggestions of things I might talk about, and was decided I would talk about the gravitational waves. However, the event you're talking about that made me famous in Spain was the results we announced in 1992 from the Kobe satellite. And I had at that time a graduate student, Luis Tenorio, who spoke Spanish very well and became a star of the media in Spain. But many things have happened since then. So I'm talking about something that's new and current, that is, but also something that's very old. Normally I'd wear my Einstein tie, which I bought in 2015 to celebrate the 100th anniversary of general relativity. And the next year, Einstein made predictions that there should be gravitational waves, and then he took it back, and so that went back and forth. And after you're hearing my talk, you want to learn more about it. There's a paper I've written with two colleagues from Mexico. The first draft of the paper was actually in Spanish, but we got an offer from Universe to publish for free, so we switched to English and wrote it in English, which would be much easier for me. And but if you're interested in the things that I tell you about that are happening now, this tells you everything that happened up until the early stages of the discovery, and then many more things have been happening, and in fact are happening right now. So it's topical because this is something that people have considered for 100 years, but only for the last 3 years have we been making observations. Okay? And as a result of that, these three gentlemen, Ray Weiss, Barry Barish, and Kip Thorne, got the Nobel Prize last year for their work on the first observations of gravitational waves. And they got it even though it's fairly early in the discovery, because they're not getting any younger. You know, we usually would like to have a little more data, but the fact is all of these guys have been working in this field for a very long time. The very first event that was observed on the 14th of September in 2015, and the LIGO, the two, one in Livingston, one in Hanford, Washington State, Livingston, Louisiana, Hanford State, 3,000 kilometers apart, light takes 10 thousandths of a second, 10 1,000ths of a second to go that distance. They were being tested, and people had gone home from testing, and the event came in the small of the night, and it was a beautiful event, even though that doesn't look so beautiful to you. It's actually a very good, strong event, considering some of the other things that they have seen. And they declared data taking happened right after midnight that night, even though it wasn't scheduled for 3 more days. So the very first run began a few days early because it was in the testing phase, but the event came in, and it was an outstanding event. And because everybody was testing, the people on the experiment knew it wasn't a false event. There's a group of people whose job it is to put in false events every now and then to make sure they're alert and telling stuff. So it leaked to some of us that there was an event. And then everybody was really quiet because the bosses said, no, you guys are not allowed to talk to anybody about this until we see it's really right or not. And so we knew there was an event. My colleague and I, we had chosen to teach a MOOC on gravity, called Gravity, but Gravité in French. Our first version was in French. We had 5,000 people on it. Our second one was in English, and we had 70,000 people sign up for that MOOC, because it was the 100th anniversary, but it also, and we were teaching it, and we knew this event had come in, but we couldn't tell the people about it. We could tell them there was a rumor. We got them on, some of the people from LIGO on, no one could say anything until after the thing ended, but we kept the website up. So he was the operating director. He's just stepped down, there's a new person coming in. But you see the two waveforms. There's the waveform of the actual data and the best fit data to it for both of the two detectors, and then the two detectors superimposed, but one flipped over and shifted slightly because of the time difference and because the angle that things were going. And this turns out to be about as good an event as you could have ever expected to have at that phase. So they were very lucky. LIGO has been lucky the whole time. Okay, so here are the two black holes, animation, and they're moving around each other, and they're distorting space-time. Because of the intense gravitational pull, they're causing space-time, and there are ripples that go out. They merge together, and they ring down, and space gets to be calm. But if you watch, there's this spherical shell going out into space, and in the moments before the merge, the strength of the change to the structure of space-time is very high. So here's the Earth. The detectors are there in the United States. The wave comes through and distorts the Earth. Okay. So it's highly exaggerated. Yeah. The Earth does not move that much. And it also moves much faster than that. You will see that it's about 100 times a second. It's getting shaped like that. And the amount that the Earth moved over a distance that was 4 kilometers was 1,000th the size of a proton. So this is incredibly precise, fine measurement. And you can see that by telling you at the top, the differential strain, the change in length of a length. So you multiply 4 kilometers times this, you will see it's 4 times 10 to the minus 21 kilometers, or you can turn that into centimeters, and you see it's a very small one. And it's very massive objects that are merging together to form a really massive black hole, and 3 solar masses worth of gravitational waves coming out. And this took place 1.3 billion years ago, but because it's at a great distance, it takes the gravitational waves 1.3 billion years to reach the Earth. So they just reached the Earth at the time they were observed. Right? And that's the thing. So that was the secret. We knew there was an event, but nobody was telling us about it, and the whole thing was being quiet. And it took quite some time. It wasn't until in the late spring, which would have been almost exactly the 100th anniversary of the time that Einstein first suggested there should be gravitational waves and support of his solutions. And then before he started retracting it. Okay, so let me review for you what happens. You have 2 black holes orbiting each other. Because they're orbiting each other, they emit gravitational waves. And as they emit gravitational waves, they lose energy and they spiral closer to each other. They go orbit faster and faster because they orbit smaller, and they radiate faster and faster until they touch, and then they merge. So we call this part the in spiral. They're slowly orbiting in spiraling. This part is the merger, and this is the ring down to make the black hole from being an ellipsoidal object, to being a spherical object. So that's the basic idea, that's the stages. And at the time this came out, it was Brexit, so I showed the original orbit in which it's detected, superimposed on England on the right-hand side, over here. It gives you an idea of the scale we're talking about. And we have the in spiral, when it gets close, the merger, and then the ring down, and that's the waveform you're going to get. I'm going to go through each part. The source distance is 1.3 billion light years, so it took 1.3 billion years for the gravity waves to get here. The one was 36 solar masses with an error of plus or minus 5. The other, whoops, doesn't say, but it's 29 solar masses. Resultant rung down black hole was 62 solar masses, and the amount going out in gravity waves was 3 solar masses with an error of half a solar mass. And that's 50 times brighter than all the stars in the observable universe. There's more power coming out of this one event for that fraction of a second than came out from all the stars in the entire visible universe. It's really a powerful event, and you barely can see it, right? So gravity waves were hard to find. Okay, and there's one other thing to notice. This is the velocity as it's orbiting. It's orbiting at a pretty reasonable velocity. Then it goes on, and just before they merge, it gets to be faster than half the speed of light. So that last orbit around, those black holes are moving really quickly. So it's very impressive what goes on in these merger events. And it takes a huge amount of distortion of space in order to make gravitational waves that are big enough to see over a large distance. Okay, so here's another thing. This is something that people who listen to birds do. They use an audiogram. You hear the frequency the bird is chirping, or whatever it is, as time goes on. And a chirping sparrow has a pitch that goes up. A bat, I'll leave this, if there were students here, I'll leave this to students to calculate. Why does a bat start at a high frequency? And it has a D chirp. It starts with a high frequency and goes to a low frequency. And it uses echolocation. But a few birds, like the chirping sparrow, go chirp like this. So I'll let you hear it one more time. That's the real frequency. And it's just shifted up into a band where humans can hear it easier. So that's the thing you look for. This is the chirp from LIGO, the chirp from Neutron, and you heard one after the other. Okay, so here's an animation of what this would look like if you had a bright galaxy with stars all around it while this thing's going around. You see the gravitational lensing of the stars in the background. You see the rippling of space-time as they orbit each other, and it also distorts the way the stars look. But as they get closer, you will certainly see when they touch, it just becomes a round black hole really quickly. Right. And so when you look at those plots again, you will find that it all happened much less than a second. That's why it's so powerful, because you have a tremendous amount of energy in a very short distance. Okay, so let me go back in history. So there was a period from around 1916 up until I think around in the late 60s, where people were arguing about whether gravitational waves were a real prediction of general relativity or not. It turns out general relativity equations look simple, but they're a 4x4 array of partial differential equations, and you can add a bunch of extra factors in it. And it turned out some of the solutions showed things that looked like waves, but they're mathematical artifacts. And there were long arguments back and forth. Were they all mathematical artifacts, or were there some? And then there were arguments, if it's a wave, it must carry energy and momentum, and therefore you should be able to detect it. And there were arguments where people imagined it. And Feynman was involved, and so were many other people. And it resulted in a young gentleman who we'll get to in a minute, named Joe Weber, actually starting to look seriously at trying to discover this. And that began a 60-year period of looking for gravity waves. And so the first 40 years were arguing about the theoretical prediction. The next time period was getting the mathematics in the right shape, but actually now trying to figure out how to detect them. Okay? And so the first thing that gave people hope, because Joe Weber actually gave people disheartened, which I'll tell you about in a minute, because he claimed to have found them. Other people then rushed to discover them. They couldn't find them. But then we had the Hulse-Taylor discovering a binary pulsar and then observing it and see that these, which have, here's the diameter of our sun, this is the diameter of the orbit. These are two neutron stars with masses that are very close to 1.4 solar masses each. And they're orbiting each other with a 7 3/4 hour orbital period. So this is very fast. If we lived in that solar system, we'd see the center neutron stars going around very quickly, 3 times a day, right? And 4 times a day. And we see that that's changing, and it's slowly making the orbit tighter and tighter because it's in the in-spiral phase. And so you can make a prediction, which is this line in here, of how the time should vary. I think this one is time. The time shift of the periapton, that is how the orbit moves around during this time period. And you see the data points. You see that they were given the Nobel Prize in 1993. I tried explaining this to the Nobel Committee. Getting the Nobel Prize disrupts your research a lot. So they have a couple of years where they don't have data, and then they got back to taking the data again. And so there's a gap. Now we have much more data, and you don't notice the gap so much. But it's falling right on the curve that's predicted from general relativity, and that gave everybody confidence that that there really was energy going out in gravity waves and you could predict what was going to happen. And in fact, LIGO was designed and built to detect merging neutron stars. That's what it was really aimed for and developed for, because we knew binary neutron stars existed and we knew what signal levels we expect and what rates. They were lucky they started seeing things sooner and more strongly than they should have, including the neutron star merger. Okay, so here's the data now from the whole example of data now from Holtz-Taylor. And you can see, you don't really notice the, well, it doesn't have the time there, but it goes down very, very smoothly. And it's still following the same thing, that it's radiating away energy and they're spiraling together. It's just going to be quite some time before they actually merge and will show up as a gravity event. But at this point, people's faith was revived that there probably were gravity waves, and therefore it was worth going ahead to try and make additional observations and think about how to do it. But let's talk about Joe Weber. This is a picture of him when he graduated from the Naval Academy as a midshipman. And he went to this early conference when people were still in the final stages of arguments about whether gravity waves are real or not, came convinced that they were, and started dedicating a lot of his time as a professor to try and figuring out how to do it. And so he started working on something that we call resonant detectors, or got the name Weber bars, even though he took sabbatical and went to Princeton for a semester and got help from several professors there, including Dyson and so forth, to come up with a good idea for a design, and he went back to the University of Maryland and built it. So here's a picture of him working on his resonant bar. And his resonant bar is very simple. It's a piece of pure aluminum, very beautifully well-made aluminum. It's very much like a crystal. It has a very high resonant frequency, and you look for a wave at the same frequency, a gravity wave with the same frequency as bar coming through, to try and excite the bar. And then the bar is hung by a steel cable, balanced delicately on this steel cable, and there are sensors all around here to look for the bar, because the end of the waves have to come to resonate at the end and then do that. And so this bar is, well, this is to say, is a resonant frequency of 1660. This is the thing I got from Yuan, Professor Yuan, one of my colleagues. This is a very famous Chinese soap opera, historical soap opera, and it says the concubine doesn't sing. Right? It means the bar wasn't singing, but if you're Chinese, you would think this is really funny. But the issue is, he kept thinking he was seeing this, and he built a second bar and put it in an Argonne lab in Illinois, and was doing coincidences between Illinois and Maryland to show that he was seeing a signal, and kept claiming there was a signal. Many other people went to look for the signals. What you're trying to do is hope that the galaxy will send out a signal right at the resonant frequency of bar, just like that opera singer can swing her voice up to get the resonant frequency of a glass. When it starts ringing, then she keeps that note, and then it will cause it to resonate bigger and bigger, and you can detect it. That's the same idea. In her case, she breaks the glass if she's really good, right? So he was working on this, and he was claiming detection, but people who did duplicates didn't see anything, and the theory said that would be an incredible amount. That would be the equivalent of losing 3 stars a year, 3 stars a year or 3 stars a week, depending on which way he was doing, out of the center of the galaxy, and that's too much to compare what we're seeing. But the other thing that's interesting, he gave the first public lecture about lasers. And he actually thought about making a laser interferometer and had students and postdocs work on it, but lasers were not ready at that time. But they understood a lot and wrote some stuff down about it. Now we're to the point where we're going to talk about the 40 years of LIGO. Okay? So this is a long sequence of people working on it and being disappointed, first struggling to understand the theory, and then struggling to try and figure out what kind of detectors and getting disappointed, and then being convinced that, well, they're still there because the whole state of binary. But LIGO started 40 years before the first detection. So that's why those guys are old. They've been working on it for a long time. Okay, so the first serious idea came from Ray Weiss, in a certain sense, but he wasn't the first person to make this. First, Weber and his students had worked on it, and there were two Russians in 1962 who had an idea, and it was revised by a very famous and outstanding Russian experimentalist, Brzezinski, and they dropped it because they weren't ready. And but Ray Weiss put in a progress report in 1972 where he said we could build an interferometer and we could detect gravity waves. But the thing that's different was that he actually thought about how to make one that could actually detect a signal that you would expect. For example, the two merging neutron stars. That's a real astronomical signal that we knew should exist. Right? Okay? And so here's a picture of him at that time, and that's a plot that I found out of the front of his report, how simple his report was. And he was funded by that time by the Air Force. Shortly after this, there was a Mansfield Amendment, after Senator Mansfield, who said the military couldn't fund research in universities, and so he had to get money from NSF, and that started a more complicated set of things going on. Okay? And so he's the first one to really address the questions of realistic noise and what you had to do to make the laser better, what you had to do about seismic no-loss and thermal gradient. He addressed these things in a set of things. And this is funny because this came as a result of the fact that Steve Weinberg, who some of you know as a famous theorist who got the Nobel Prize for the unification of electroweak forces, was a professor at MIT at the time, and he was teaching general relativity and gravitation, which became a book that he wrote, and then he wrote the first 3 minutes. And he and his wife got a job offer from Harvard, so they moved next door. They didn't have to move out of their house. And so they asked Ray to teach the course on general relativity. So if you get requested to teach a course, sometimes good comes out of it. And he couldn't understand what Weber was doing. And so he had special meetings with some of the students where they talked about how they really do it. And that was an outgrowth of talking to the students, figuring out to make a laser interferometer. And that turned out to take up a lot of his time for the next 40 years. Okay, so these three people are the ones that started LIGO. Kip Thorne and Ray Weiss met, and a long story in that article I did. They met at a conference and struck it off. But Kip Thorne's a theorist, and so they were trying to get Brzezinski out of the Soviet Union, but they could not. And so Ray Weiss suggested that Ron Drever, who had a reputation as a very good experimentalist and gotten interested in gravity waves because of the things that were going on, do that. Now it turned out they hired him to Caltech, and then for the next several years, Drever and Ray Weiss were fighting like crazy. That became a problem. And Kip Thorne couldn't mediate very well between them because they were fighting over experimental issues. That actually slowed things down for a while, but that's a situation. And then finally, the NSF forced Caltech to put in a project manager. And unfortunately, he picked somebody I knew was also difficult to get along with, so you had a three-way fight going on. And then they replaced him with Barry Barish, who really understood how to do things and made it so that the scientists were separated into the science team, and then there was the instrument team, and there was a phased, first generation, second generation, so a set of stages. You'll see it very similar to what's done in hydrogen physics. You're building a detector, you get it up, you run it at the LHC, you do an upgrade, and so forth. And you see that model in LIGO. LIGO is born. There is Kip Thorne and Drever at that time, and Ray Weiss at that time. And you see a little curve stating what they're going to do. And Caltech and MIT being involved with the National Science Foundation funding that. And I did an early review of this, and the first draft cost was very small. The second, 330 million. The second draft was 100 million. You'll see by the end it was 600 million before the whole thing got done, because it took first LIGO and then upgraded LIGO before any detections were done. So there were two stages, and the first one cost 300 million, and the second cost 300 million. And at the same time, the Europeans had been called upon to review a proposal by Ray Weiss for this interferometer, and they said, hey, this is a really great way to go. We were tired of the bars. Let's do that. And so you'll see there were two groups, the German colleague group, and then a later group, which eventually ended up making Virgo, which involves many of the people in Europe to build the Virgo detector, which is now operating. NSF gave money in stages to do a study, and then to do funding for a joint effort to prepare, then eventually getting Barry Barish in place, who really set the thing up. They had a first initial set of operations from 2002 to 2010, and then they were shut off for 5 years for the upgrade. You know, for most people, 5 years of being turned off is a really long time. I mean, it's, for me, it's and then they began operating in September, right? A little earlier than they were supposed to, by a few days. But they didn't begin operating again until 2015, but immediately started making discoveries. And that's the big thing, and that's the 620 million to date. And it's going to be more because they're going to get the upgrade again because they're making great discoveries, right? That's the thing. So we'll see what happens. Okay, so here is the 3,000 kilometers apart, and there are the pictures. One's in a pine forest, sort of swampy pine forest. One's in a kind of deserty region in the state of Washington. And
a laser beam is split and set down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
And you add them together, you get nothing. You get a zero, big fat zero. No light gets detected at the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave is passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
Sounds pretty easy, right? It's a little more complicated than that. So I have another video that's made by the Virgo group, and so I think it's a Dutch accent, but I'm not sure.
In an interferometer, a laser beam is split into two beams. Mirrors reflect the beams, so they meet again at the starting point. If now the distance to each mirror is exactly the same, no light will be seen by the detector. The waves of one beam extinguish those of the other beam. This is called interference. A passing gravitational wave distorts space, making one arm slightly shorter and the other arm a little longer. The light waves do not cancel each other anymore, and we now measure a tiny signal in the detector. Now we add an extra mirror in both beams. In this configuration, the beams bounce hundreds of times back and forth between two mirrors, before returning to the beam splitter. The intensity of the light in these so-called Fabry-Perot cavities increases substantially. The cavities boost the interference effect a few hundred times. The sensitivity is further increased with two additional mirrors, which recycle the outgoing light into the cavities, and with a so-called mode cleaner, which removes disturbing noise from the laser beam. The light power in the cavities is increased to hundreds of kilowatts. Even more complex optics and electronics are required in order to keep the mirrors properly aligned and in position. Ground vibrations at most about 100 nanometers are nevertheless millions of times greater than the vibration caused by a gravitational wave. Therefore, all components are mounted on horizontal and vertical vibration attenuators, the best in the world. While the ground is trembling, the mirrors and beams feel nothing of it, thanks to the superattenuators. Also, air presents a problem. It gives rise to unwanted vibrations, such as due to sound. Four so-called cryogenic traps provide an ultra-high vacuum quality. Up hundreds of times more signal of a gravitational wave by extending the Fabry-Perot cavities to 3 kilometers. This and much more is needed to realize an interferometer for detection of gravitational waves.
Okay, it's a little more complicated, right? And in fact, if you look at how LIGO was originally designed and how Virgo followed along that, it's designed to have its minimum noise in the region where you expect spiraling neutron stars, neutron star pairs. And in fact, the black holes are heavier and they have a lower rotation period and they're lower frequency, and so you see them less often. But when they say many times the wave passing by, you're looking at stuff that is at 100 hertz to 200 hertz range, and it's lasting less than a second. So you're getting like 100 oscillations or less for these times when the signal is big enough to observe it. And there are a lot of things that are done, but you're essentially limited by the uncertainty principle. You're measuring the position of mirrors that are set out at big distances. You're measuring lengths, but you're measuring basically positions. And so there's a delta X, delta P, and so it has to do with the photon counting noise and the photon noise. So the power in the laser and the mass of the mirrors were set in terms of what's going on. There's another thing which you'll see, only briefly because I'll run out of time, is that the seismic noise from the ground, even with those isolation things, was very difficult. So a major contribution from the Europeans was figuring out how to make triple pendulum isolation towers, that is, multiple levels of isolation. That's that team. And that Fabry-Perot, where you saw the mirrors kind of focused to a narrow waist, that was Ron Drever's idea. And Drever and Ray Weiss, who wanted to send the beam in slightly into the mirror and ricochet back and forth 100 times and come bounce through the same hole. That was Ray Weiss's idea. And they fought over that for a couple of years. But eventually, Drever's idea was accepted by other people. But Ray's still not happy about it. It's a funny kind of thing, but that's what it took to get to this level. Okay? And that means you really had to believe this is a really important thing, and that first that gravity has existed, and it's really important to detect it. Now it turns out that's right, but 40 years is a long time to be doing this. Okay, so here again is the black holes, but underneath them is a distortion in 2 out of the 3 dimensions of space, so you can see. And you see space is distorted. There are lines that show you the path of a particle if you dropped it there, freely. So the black holes are orbiting around. They're black because once you get to the event horizon, you can only go inside, you can't come out. And we'll slow the thing down as they get closer and closer. You'll notice we're now a quarter of a second, or a fifth of a second. And it's distorting space in quite substantial ways. But as they get very close, you'll see the distortion looks very funny. But if you watch the black holes themselves, you will see there are actually 2 event horizons. There's an apparent horizon and a particle event horizon. And right there, you can see the apparent horizons overlap and they're merged. But there's another horizon inside, and those have to merge too. And so this is something that gets black hole information freaks all excited, because there's a chance, if you can measure these things precisely enough, to try and figure out what actually happens to those horizons. Right? But that's the idea that you can start testing general relativity if you get good enough set of data. You can test general relativity in a strong field limit. You're going to see we also now have some tests of general relativity in the weak field limit as a result of these events. And I'll try and get to that. And so here are these events, and numerical relativity means one of the big advances is that we've learned to put Einstein's equations onto supercomputers and crank them and be able to make arrays of different kinds of different masses of black holes and different spins of black holes and put them together and then look to see which ones fits the data the best. And that's just a big computation problem, but that's what you do in order to find what's going on. Okay? So now the other thing, imagine you have two detectors and you know the relative time of arrival between those two detectors. There's a circle on the sky which gives you that difference in arrival time. If it's the same exact time, there's a circle that splits the place in between. Right? If it's a different one, it's a different circle on the sky. So you'll see this is a circle on the sky of that first event, and it peaks in one direction because these antennas have a quadrupole response. That is, they're sensitive in this direction, not sensitive at 90 degrees, sensitive again with every 90-degree fold. So you can actually determine, but that's a huge fraction of the sky. You go to your astronomer friends and say, this event happened here, go look for it. And they say, how many square degrees is that? You say, it's only 1,500 square degrees. They say, our telescope, we can't see bigger than 1/10 of a square degree, at the best. And our biggest telescope, some telescopes now can do 2 or 3 square degrees. So that's a hopeless place to look for it. That's why it turns out Virgo is so important. So LIGO and Hanford were on the air. They made the original discovery. Turns out, I'll show you, they made some more discoveries. And GEO, which was the German version in Hanover, is only 600 meters long, and it's not sensitive enough. But Virgo was slow being upgraded to upgraded Virgo, and they didn't get on the air for almost a year. It's almost over, not until September of 17. And so Virgo is 3 kilometers instead of 4 kilometers. There is a underground superconducting, sorry, it's not super cooled, the mirrors are cooled to make the noise less, called Kygra in Japan, and they'll come on. An agreement has been signed between LIGO and India for India to build another detector. And there are discussions at other places, but we know that right now we have 3 good detectors that are working most of the time, 60–70% of the time they're on, and another one that we think will be a very good detector coming on in about a year. So then it'll be better. And the more you have, you'll see the more you can do. So that's what the future is going to be. Short term, there are going to be long term more things that happen. And I think Kygra is a prototype for what, if you really make some exciting discoveries for what you might do with a large underground, 8-kilometer long underground kind of detectors. But that's big and expensive and further in the future. Okay, so here's the basic idea. The original LIGO could see out to this sphere that's shown there in red. I think I have a way to blow it up. Okay. The advanced LIGO is out to this sphere here, and now it's actually been shut down and improved, and the sphere is out to here, but when it gets the full set of improvements, it will be a sphere out to there. And so every time you increase the sensitivity a factor 2, you can see twice as far away, but it means you see 8 times as much volume. So we should expect the current version should be getting 8 times the rate the original version did. Now I'll show you what the result is up until a month ago as we get to the end of the talk. So I wrote this talk up and I gave this to Nobel Committee people shortly after this happened at a public forum or something like that. And just as I was writing the thing, this cartoon appeared, right? And it's the sound of black holes being repeated. You know these guys are graduate astronomers because they have a telescope, but really they're doing it on the computer. And you know it's the guy outside pounding on the pipes, right? But it turned out the day after this cartoon appeared, there was another event.
1.4 billion years ago, 2 black holes performed a cosmic dance. They spun around one another, coming closer and closer together until finally they collided. This dance created ripples in the fabric of space and time, also known as gravitational waves. In December of 2015, those gravitational waves reached Earth and were detected by an instrument known as the Laser Interferometer Gravitational Wave Observatory, or LIGO for short. Scientists with LIGO announced the detection of the two black holes on June 15th.
So this is the Christmas one. The day after Christmas.
This is only the second time that scientists have ever directly detected gravitational waves. The first detection, also made by LIGO, was announced earlier this year. Currently, all other telescopes and space observatories study the cosmos by collecting light or other particles. But the black holes detected by LIGO are not expected to radiate light. So by looking for gravitational waves, LIGO is illuminating otherwise invisible sectors of the universe.
The last part's an ad.
For Space.com, I'm Calico.
Okay, so this Christmas, the day after Christmas, coalescence was pretty well observed and pretty well understood. It's lower mass, therefore you have signal for a longer time because it's spinning, it's orbiting at a higher frequency. Right? Because the black holes can get closer together before they merge. So it's faster going around. So you see it goes longer, and it has being 21 solar masses as a result. And again, the best fit was a spin. It was about 1/5 of the maximum spin that a black hole theoretically can have. Okay, and so if you look, the first event, you hardly had any stuff to it because it was out of the wave, out of the frequency bin, which you could see it. You could see just a few. There was a possible event detected, and then this event that was detected, it went on quite some time. That you can measure the frequency, and that frequency is actually the reduced mass, the proportional to the reduced mass of the black holes. You can figure a lot of things out by just knowing what's happening. And so this tells you the masses of these events and what was going on. And this is more technical details than you want, but this is in case somebody was taking notes. Okay, so how do we know what we saw? Well, here's the best fit, and they said GW16, but I write in 15 because it was 15. And you see these events and the best fit for them, and you see what a binary neutron and spiral should look like, much higher frequency. So you could tell this is heavier than neutron stars because the frequency is high, the frequency is lower. So you can see what's happening. That's how you know what's black holes. And you scale the mass. Everything gives you information about what it is. And the amplitude of what you said gives you an idea of how far away it is. Okay. So here was the data. They turned on a little early, right? They extended the time to it was going to start here, then they just started it there. There was a possible event there, and there was an event right before they turned off for an upgrade, and in January. And that was the first run. And I'm waiting and waiting for the next set of events, and they don't come for a while. But you can see where they appear on the sky, and the problem is those are huge areas on the sky. You cannot do astronomy to think, is there anything left over? How can we see whether there was anything going on interesting? Well, those are such big fractions of the sky. You just can't use a giant telescope to do it. Okay. However, if Virgo were on, you could reduce the error down to something like the green thing. That was why we were so eager for Virgo to get stuff fixed and get on the air, so we could see what was going to happen. Okay. And it did, finally. It started in September of 2017, and upgrades had been made both to Livingston and to Hanford, but they couldn't get the laser stable for Hanford, so they had to actually go back to the old laser. So it didn't upgrade as much. So you can see for this thing, the signal here at Livingston is very good. The signal from Hanford is okay, it's an event there, but the signal from Virgo is barely detectable. But having that extra thing does allow you to pick where in the sky it's going on. And so here's a picture of Virgo. It's an agricultural field, so occasionally you'll see pictures of it with fields being grown there, sometimes green fields growing there, and there's an irrigation canal. So this is the Virgo detector, and you can see it's 3 kilometers and it's above ground, and it has to be protected from the things around it. Okay, so with Virgo there, instead of having this big banana, you had two regions. The first was the green one, that's what came out in the telegram, and then when they did refine fits and everything, you got the gray area as the best estimate of where to look in the sky for that. So that was very important, that event happened, because something exciting happened a little later. And let me get on to that. So this is the, you know, the size of the region in which you would have to be looking and so forth for those events. And here is what we knew, and this is a problem I was worried about. Why are they seeing these heavy black holes? Because everything we've seen up to date were black holes that were down in this region. You see binary stars, which is a black hole with a star orbiting around it, and it's emitting material that's going into the black hole, and before it goes in the black hole, it emits X-rays, and you see it as an X-ray binary, and you can estimate from the orbital parameters the masses. And they're all down here, and all the LIGO black holes, they're up there. Right? That seems different. So that's a problem I've been worrying about for some time, and people are making up different models for where this could be. And this is just to show you, I don't think I was spending much time on it, but this is to show you the frequency. This was meant to have, the long-range design was meant to have a minimum here in the range 200 to 300 cycles per second, or hertz, in order to be where the neutron stars would fit. And this is where the various detectors are, you know, LIGO and the two different ones for Virgo. I have another one that sort of shows you where they were at the beginning of the advanced runs. And you can see that they made improvements to the Livingston detector that let them go to lower frequency, but the improvement to the laser and the other things and getting rid of some of these spikes did not happen. Virgo's still in the early stages. One of the things you have to do with this big, long detector is you've got to go in and put dampers on all the things that can vibrate at, you know, harmonic frequency. This is like when you pound the table. Some frequencies show up, you know, you've got to damp those out so you can see the kind of stuff. But you leave one in there, which is the resonant frequency of the mirror, so you can get the thermal noise of the mirror to go in that resonant line, and then you take that out of the data, you smooth it out, and then you fit it and bring it back. So there are a lot of tricks that they do, but it takes a long time to learn how to build this and make it work. Okay, so they're not the only ones doing it. They're the ones that made the first success. There are, if you look at a function of frequency, or head wavelength across here, you can look with laser interferometers in the range of around 100 hertz. If you put detectors with very long baseline, 3 million, 5 million kilometer baselines in space, the laser interferometer in space, then you can go to things with much longer wavelength, therefore much lower frequencies. And there are proposals to do that. It's called LISA, Laser Interferometer in Space Array. And the United States, but particularly the European Space Agency, is pushing to build this. And the Chinese are pushing, there's two different groups in China pushing to build such detectors, and I think that will happen. There is also neutron stars in orbit, and some of those neutron stars are binary, are pulsars, not just binary pulsars, they're pulsars, and are extremely stable clocks. And if gravity comes by, it will move them closer and further away, and you can see the arrival time of pulsars change. So there is a big effort in pulsar timing array, and there was a thing I referred to that was almost 3 years ago, is to look in the cosmic microwave background for a particular pattern of polarization that would indicate gravity waves, which are particle waves, couple to the polarization of the microwave background and produce a signal that you could expect to see. And that would be telling you what is the energy scale of inflation in the early universe. Mm-hmm. And so we thought for a while there might be a detection of that, but then we realized it was in a region where the galactic magnetic fields give you the same kind of a pattern. So it's not clear what the situation would be. So far, the only place we have confirmed results is here, but we're still waiting to hear what's going to happen on other things. It will certainly be some years because of ESA's budget. It means the launch of the European version of LISA won't happen before like 2034. So it's like the people working on it are kind of, you know, they're excited by the field, but they're dismayed by the fact that it'll be a long time before they'll get their data up there. And here again is another thing telling you where the signals might come from. The Big Bang, from the supermassive. In the middle of every galaxy that we've measured, there's what we call a supermassive black hole, something between 10 to the 6th solar masses and 10 to the 9th solar masses. And if two galaxies merge, eventually those black holes get together and become a binary, and they produce a big signal that you can expect to see. And so those are the kind of things you can see. And there are compact binary mergers that we can expect to see. That's what LIGO's been seeing. And there are also some other events that you should be able to see as LIGO gets more sensitivity. Okay, and here's one thing that people realize originally. We didn't expect, at least some of us did not expect, there would be 30 solar mass black holes out there. But if you take a bunch of 30 mass solar black holes and evolve them together, you will find that if you had LISA or ELISA up, it would be able to detect them for about 10 years before they're getting to the point where they're going to come into the LIGO band. And you can predict within a few seconds when they're going to merge and where they are in the sky, because you've got to observe them for 10 years, you're orbiting around the sun, you get a pretty good angle on the sky from where they are, so you know what to do and where to look for them if that should happen. So this is something that you hope would happen when the laser interferometers get in space. Okay, so this is more of the same thing. I want to go on to the... So what are the applications? Well, I mentioned one that I worry about a lot. All the known black holes from other sources and from the neighborhood are way down here below 20 solar masses, and all the ones from LIGO are up here in the 20 to 30 solar masses, plus the merged ones are higher. And so I spend a lot of time worrying about this, and I have proposals about that, but that's secondary to what we're doing here. But the other thing is, all these things allow you to do tests of general relativity to first order, and then there's post-Newtonian first, second, and third order kind of expansions you can do to test as general relativity the correct theory, or is there some small variation coming in. And you can see here's 0 deviation, and it's all consistent with general relativity. And this is one of the things, and there are a couple other things that let us know it's going to be extremely difficult to modify general relativity to try and take care of some problems that people don't like. So a lot of my work is in cosmology. We have black holes, we have the accelerating universe, we have a lot of stuff. People try and account for that with modified gravity. It's going to be very difficult to do that. There are a lot of constraints on that, and I'll point out another one and so forth. So why is this important? Well, it's the first direct gravitational wave, which was the last big prediction of general relativity. It's the first observation of a black hole binary and the formation of a black hole. Not only do you have two black holes orbiting each other, but they merge and you form a new black hole. There is physics that go on when a black hole gets created, right? And it's the most, we used to say gamma ray burst was the most powerful things that happen, but this is more powerful than any gamma ray burst. We'll see that first event that was done. So it's a new window in the universe, so it's a big deal. So you think everything is great, it's new era from astronomy, but LIGO got lucky again. And so it's not just black holes.
LIGO's hits just keep on coming. After its first detection of merging black holes, swiftly followed by finding 3 more, and then a Nobel Prize, the pair of gravitational wave detectors has made yet another huge discovery. On August 17, 2017, the observatory detected gravitational waves from 2 neutron stars spiraling together and merging. Just 2 seconds later, a so-called gamma ray burst was detected by NASA's orbiting Fermi Gamma Ray Space Telescope and its Swift Space Telescope. 12 hours after the wave was detected, a team from Las Campanas Observatory in Chile reported a new glowing optical source in galaxy NGC 4993 that was consistent with these findings. And with the advanced tip from LIGO, both radio and X-ray emissions were found a few days later, coming from the same neighborhood. Not only is this the first time LIGO has detected gravitational waves from a neutron star collision, it's also the first time that electromagnetic observations from conventional telescopes accompany the gravitational waves. At wavelengths ranging from ultra-short gamma rays to very long radio waves, the event was seen by observatories around the world. Because we now have visual information to go along with the gravitational waves, new discoveries are being made about the nature of neutron stars. The light coming from the collision showed spectral traces of lanthanides, a group of heavier elements towards the bottom of the periodic table. This strongly suggests that merging neutron stars have been responsible for the creation of heavy elements such as gold and platinum, a long-held theory. Not only that, but the shape of the gamma ray burst was unusually weak. Gamma ray bursts are usually so strong that researchers assume that the gamma rays emerge from two back-to-back jets that shoot out of an explosion like narrow spotlights. The weaker gamma ray burst suggests it was produced when broader jets slammed into a cocoon of matter surrounding the merged neutron stars. While this finding is home to a lot of firsts, it won't be the last. Researchers are positive that with the large amount of gamma ray events out there and the increase in both gravitational and electromagnetic detector sensitivity, we'll be seeing a lot more of these combination events in the future.
And one more movie celebrating this event.
For the first time, astronomers have detected a single cosmic cataclysm in both gravitational waves, ripples in space-time itself, and electromagnetic waves, what we typically call light. This hugely collaborative effort includes the LIGO and Virgo gravitational wave observatories, along with a multitude of telescopes in space and on Earth that, together, collectively monitor the full spectrum of light. The spectacular event was produced by the collision and merger of two neutron stars. These objects are the burnt-out remains of giant stars that have exploded as supernovae. They leave behind cores of exotic matter composed primarily of neutrons crushed together under the intense pull of gravity. More mass than our sun is compressed into a sphere that is about the size of a city. Astronomers have long known that neutron stars are found in pairs, orbiting one another. The theory of relativity predicts that the motions of these incredibly massive objects should generate gravitational waves. These waves would drain energy from the orbiting bodies, causing them to slowly spiral together and eventually collide with each other in a spectacular explosion. On August 17, 2017, a gravitational wave, CHIRP, was recorded by the National Science Foundation-funded LIGO observatories, and less than 2 seconds later, a short burst of gamma rays, a high-energy form of light, was detected by NASA's Fermi telescope. Researchers quickly realized these two fundamentally different types of waves could have come from a single neutron-star merger. If so, it was critical to identify exactly where this had taken place in the sky, and if the explosion could be seen by other telescopes. The Fermi data indicated the burst came somewhere from a patch of sky covering about 1,200 square degrees, an area equivalent to 6,000 full moons. Adding information from an independent gamma ray detection from the integral satellite, the search area was further reduced. The LIGO observatories placed the source somewhere in long, narrow strips of the sky, one of which overlapped with a target patch. The Virgo Gravitational Wave Observatory in Italy, working in conjunction with LIGO, should easily have been able to detect a signal of this strength, but saw almost nothing. This was an important piece of the puzzle, since any gravitational wave observatory has a small number of blind spots where it cannot detect an incoming signal. Restricting the source location to Virgo's blind spots further narrowed the search area down to approximately 28 square degrees, or 140 full moons. Around 50 candidate galaxies were identified in this area for follow-up observations using optical telescopes. Less than 11 hours after the first detections, astronomers using the Carnegie Swope telescope identified a previously unseen blip of light in the outer reaches of the galaxy named NGC 4993. Several independent confirmations were reported from other telescopes over the next hour. The first ever optical counterpart to a gravitational wave event had been found. Knowing exactly where to look, astronomers began an unprecedented campaign of follow-up observations using more than 70 telescopes around the world and in space. During the course of the next 2 weeks, the neutron-star merger was detected across the entire electromagnetic spectrum. The gravitational wave data have, for the first time, provided a direct measurement of the masses and orbits of a neutron-star pair before their collision and merger. The data also enabled ongoing follow-up observations across the electromagnetic spectrum, characterizing the explosion and revealing how such unimaginable events have played a formative role in shaping the world around us. These results, for the first time, confirm that neutron-star mergers create precious elements like gold and platinum, as well as a host of other heavy elements all across the periodic table. Explosions like these, through our cosmic history, have seeded the universe with the materials that later would form new stars, new planets, and beings like ourselves who look up and wonder.
Okay, so it's a big deal. They were really lucky because it was close by and easy to see. but it's not that far away. And again, you get the test gravity because you see the time it took the gravity to get here and the time it took the electromagnetic wave was less than 2 seconds different. And you would expect there to be a delay because it takes a while for the neutron stars to coalesce and form relativistic jets to provide the signal. And that's the argument about it. So it's very hard to modify gravity given those constraints and the solar system constraints. So I have a couple more if you guys don't want to. At some point I'll stop and answer questions, but I thought that it's nice to show in Spain some pretty pictures. I think it's either this one or the next one that shows you can make art out of science. When two neutron stars merge, a lot of stuff happens. It's really quite spectacular. And we should be able to convince the Spanish government to fund study on this, because we can tell them exactly where 3 Earth masses worth of gold is. It's just a little far away. So, you know, that's pretty artistic. I think this one, unfortunately, has beautiful music too. But and it's actually very complicated because the neutron star is not simple like a black hole. It's made of much different materials. There's an outer surface, there are magnetic fields, there are many things. That's why you get light from it. There's material left over and things aren't working. Jets form, they don't, the simulation goes there. You get these relativistic jets, and that was the argument in one of the earlier ones where they speculating that instead of these narrow pencil beam kind of jets, they were broad jets that couldn't get through this extra material on the outside, and that's why it was so much different. It's less than a factor of 100 as bright as the typical gamma ray burst of this thought to come from the government. And so this is just pictures of it. And here is the Day of the Dead picture that came out, literally came out on the Day of the Dead, of the known neutron stars, which are the death products of stars, and of the black holes. And the purple ones are the ones that are known from X-ray binaries, and the blue ones are the ones that are known from LIGO. And so, as of April 1st of this year, the improved graduation detectors have been up and operating for LIGO, and they're making new discoveries. They're getting a discovery about every week. So I can show you that. Here's the run, the first 3 events that I showed you before, in terms of what they were. The next run, where I was upset because they weren't getting any events for such a long time. And then finally, right near the end of the run, they got a bunch of events, including that neutron star merger. And it's very close, the neutron star merger. It's extremely close here. But remember, Virgo didn't see it, but Virgo saw this event. So it happened just a couple days before. So it was proof that Virgo was working. So that was very important, right? But now as thing turned on for run 3, and again they think they have another neutron star merger, and maybe a neutron star black hole merger. Since this graph was made, there have been at least 4 more candidates, probably 5 more candidate events appear. They're appearing about 1 per week in terms of what's going on. So the improvement, while they were shut down, there's a little gap there, but it was quite some months in between. They did improve the detectors and their performance. and they are detecting them more frequently. So we should be expecting new results coming out regularly, and some of them are going to have importance in terms of our understanding of the universe. Some of them are going to become routine, right? Yesterday's great discovery is tomorrow's calibration is the next year's noise. It's the progression of science. So I'll stop here and try and answer questions.